Okay, as usual, some announcement quickly. For your lab test 1, I will try to release the marks for you by Friday this week. Hopefully much earlier than that. Hopefully Thursday, Wednesday-ish, but definitely by Friday, you will know the result. I'll tell you exactly how you can check the feedback, both the written part and the programming part. For lab number 3, it was released yesterday, but you can definitely start today in the lab sessions. I will be there to help you. And if you really need some help on the Java collection, especially array list and hash map, so I do created some tutorial videos for you. So you can go over them first before you actually go ahead and program. I will try to add more collection type, maybe throughout the semester, so you can learn more about Java collection. It's just that we wouldn't cover them in the class. They're rather straightforward. It's just several new syntax you had to pick up by doing the labs. Okay. Now let's go to our lecture part. Okay. Today, basically, we're going to talk a little bit about math. Okay, math, and then we try to link the math to analyze your programs. So it's rather useful, towards the second half. But for the first half, to bring every one of us up to speed, we need some math foundation. But it's not really rocket science, very easy to understand. Okay, let's see where we are from before the reading week very quickly. So we talk about one approach to assess whether method number 1 would be more efficient as opposed to method number 2 is by simply running some experiments on some physical computers, which means you have to write down your Java code that compiles and then to run them on machines and then to see for different input sizes how long it would take, right? That's basically what we said before the reading week. So now after the reading week, we're going to just review our criticism about this particular first approach. So what's really disadvantages for this first approach by running actual experiments is, first of all, you have to actually finish the Java coding right away before you can run the experiments, for sure. Okay? Finishing your Java coding will take some time, rather than saying, maybe I'll just sketch the idea on a piece of paper and then to analyze the complexity between the between the two algorithms. So that's one drawback. And the second thing is, it's about the being really comparing apple versus apple. So you want to make sure you run the experiments on exactly the same execution setup, the same hardware, the same operating system, and the same process load for your computer. So it's not that easy to control. Okay? We deserve a much more scientific way to do it. Okay? Which is we want to somehow, rather than measuring exactly the running time, like over here, let me give you some intuition. Rather than saying it will take about this many seconds to run the first one as opposed to the second one, we're going to assign some mathematical function to each one of them, and then to try to analyze the running time on the paper. Okay, that's something we're going to do for this lecture. I'll give you all the mathematical foundation you need, but it's very simple. Okay, but there's some proofs we had to go over together. Okay, so now a better way to do it, we want to talk about relative. So here, when I say relative means we simply don't have to worry about the exact running time, like how many seconds. We don't have to, okay? And then when I say high-level description, it could be in Java, but it doesn't have to be compilable. As long as we can see the idea. We see, oh, you have a loop over here. You have some if condition over here, so we can start analyzing. It doesn't have to be 100% compilable code. Okay, and then we can definitely talk about different input sizes. Well, so these are the 3 ingredients we're going to learn today. First of all, we have to learn about the notion of primitive operations. Okay, I will define exactly what primitive operations are for the purpose of this course. And then we're going to see how we can turn from primitive operations to the relative running time according to your input size, second thing. And the third thing is we have to focus on the worst case. Okay? So basically there are 3 kinds of cases you can consider, either average case, best case, or worst case. We'll see why we need a worst case. Okay? There's a reason behind that. Okay? We'll get there. Now, let's go right to the subject, step number 1. How do we count primitive operations? Let me define exactly what primitive operations are, and let's do some fun exercise together. Okay? Let's see, first of all, let's define. Okay, first of all, you should understand, when we talk about a primitive operation as opposed to sophisticated one, each primitive operation is going to take some constant number of time, which is very small. And it doesn't matter which platform you're using, pretty much the same, maybe 1 millisecond or even shorter time. Let's define. Let me give you a list. The first one, assignments. So if you assign some value into some variable, it's considered as primitive. Very easy. Fetch the value from the memory, assign that to another memory. Okay. Second one, indexing into an array. As we learned before, if you want to go to a particular slot of the array, it's very easy. Calculate the address accordingly and go there. Go to a particular memory location. And any of the arithmetic, like a plus, minus, multiply, modulo, relational, greater than, less than, any relational operator that will give you a Boolean expression. And also logical operation, which is like the conjunction, disjunction, also negation. They are also primitive, very easy to apply. And we also got, if you want to get access to an attributes, let's say if we got a class called accounts, I want to go to the attributes called balance. Also very easy. I just want to go there. Go to the object and go to that particular attributes. Also primitive. I have a question before that. And final item in the list, if you want to return a particular value for this particular accessor method, it's just a return. That's also primitive. Also very fast. And did you notice that there's something missing here? Okay, let me ask you. Method call is not here. I might say account acc.n. N is simply a method, right? So can I actually make a very general argument to say whether a method call in general is very efficient or inefficient? Or it depends. It depends, right? Exactly. It could be as easy as hello world, which is very cheap. Can be as expensive as you want to sort a million integers. So now my point is, I didn't include a method call as part of the list for primitive operation because for method call, you have to judge case by case, which we'll do. We actually analyzed quite a few methods today to see how the running time can be different. Okay? So now, any question about this list before we do one exercise right away together? Okay, if you need any reminder, just tell me and then I'll go back to this list. Okay? So now, what we're gonna do in the next slides, yes? You mean which item there?
Like the account.
Oh yeah, of course, yeah. Apparently, when you say acc.balance, acc is a reference type, right? We go to that object there in the memory and go to its attributes. Okay, so in the next slides, we have to be very, very precise. Okay, even a difference of 1 is not acceptable. Okay, let's be very precise. Now, I want you to have a quick look for 30 seconds on this fragment of code. Not difficult. We want to find a maximum from some array. There's only one small detail I want to show you. You can see we have an integer array A, which can be of arbitrary size. And then we simply give some redundant parameter over there. It's simply the size of A. Okay? I'll show you one example in just a moment. But have a look at the lines of code. Make sure you're familiar with it, and then we'll try to count. I'll lead you to that. Okay? All right. Now, our eventual goal is to know exactly, in the worst case, how many primitive operations will be executed from this fragment of code. That's our goal. But let's see how we can approach it. I will give you 2 leading questions for you to help you. Question number 1. Can you tell me, look at line number 3. Line number 3, and then I'll show you on the iPad here. Look at line number 3 and look at this expression over here. I less than n, which is a state condition for this loop. Can you tell me exactly how many times this expression will be evaluated? Exactly how many times? I heard n minus 1. Any other answer? N, okay. Anyone else? It's either n minus 1 or n. As I said before, when we are counting for precise number, even 1 difference matters. Okay? Let's see exactly. Okay? Remember what the purpose is for this particular state condition here. Okay? I less than n. Okay? Let's just give one example. How about that? Let's say I want to say find max, and then let me just put, it's not exactly legal Java syntax, but let's live with that for now. Let's say I got, let's say 2, 1, 4, and 5, for example. And then I'm going to pass some redundant operator, so I can say 1, 2, 3, 4, just 4, the size. Okay? And we know that the answer should be 5. Okay? So now in this case, how many times are we going to evaluate this expression here? In this case, n is simply of value 4. Is it 4 times or 3 times? Okay? How about we try? Okay? Let's say when I is equal to 0, I less than n, in this case, I is less than 4. We know that it is true for the very first iteration. That's why we stay in the loop. I gets incremented for the second iteration, get to 1, that will remain to be true. That means we go on to the second iteration. And then go to 2, and then that will still be true, go on to the next iteration. And 3 over here, we know that it will still be true. That means go on to the 4th iteration to look at the last number over here. Now, what's going to happen after the 4th iteration? We increment I further to be 4. But do we still evaluate this expression here? Do we evaluate it or not? Either that's true or false is another story, but do we evaluate it? We do. Exactly. In that case, it will give us false. That's how we exit from the loop. So that means 1, 2, 3, 4, 5. 5 times, which is exactly n. Questions? Yes. I starts from 1? Oh, yeah. One, two, three, 4. Let me just double check if that's really what I intend to do. If that's 1, actually you might be right. If I is, okay, let's stick with the code, that's good. Okay, if I start with 1, that means we got exactly 1, 2, 3, 4. So that should be 4, right? Good. You know what? That's interesting because I'm not sure why I changed this. If I put n over here, guys, sorry for making a change on the fly. How about this? I do notice your point. In this case, of course, it's only 4, okay? But to really make whatever I've explained so far make sense, can we just pretend? I'm going to change this as well, okay? This should be 0. Actually, you know what? Even that, 0, 1, 2, 3, 4 is actually 5. No, you know what? Why am I keep confusing you? This is okay, because the size of the array, size is 4, right? However, the starting value, what I said before, there's only one thing that's wrong from what I said before. The starting value for I is 1. So that means this row shouldn't exist. Okay, I apologize. That's my fault. Okay, so now let's do it very quickly again. So the starting value for I is simply just 1, not 0. So that means we start with 1, is true, increment to 2, true, and then to 3, also true. Okay, and then when we go to the last, after the last iteration, we'll actually increment from 3 to 4, and we evaluate that for the last time, right? Okay, that's why we just get 4. And 4 is exactly equal to the size of the array, so that's n. Okay, any confusion, please?
So it evaluates the issue 3 times, right? But it doesn't.
No, evaluation is 4 times, but the first 3 times is true. That means, yeah.
But all the evaluations matter, so we say 4. Right?
Yeah, that's why, yeah. Because I simply ask you how many times is I less than n going to be executed? It's going to be corresponding to the size of the array. Yes, question?
If I goes up to 4, then wouldn't my 5 have an array out of bounds exception?
No, you wouldn't get array out of bound exception in this case because you can see that we simply say after this iteration over here, we increment I from 3 to 4, right? And remember, every time after the increments, you have to recheck the state condition again for the loop. In this case, 4 less than 4 is false. That means you never get a chance to go into the loop body again. Okay, that's why. Okay, any more confusion before I move on to the second question? So the first question is, it's going to be exactly n times for evaluating this expression over here, exactly n times. Yes? Yes? Yes. So now what we're trying to say is, what's the worst case? The worst case could be, Skip the first one. Yeah, yeah, exactly. It's going to skip the first one. So we start with index 1, and then index 2, index 3, and then when we increment to index 4, index 0, 1, 2, 3, 4. 4 is 4 less than 4 is the false case. We still evaluate it, but we just wouldn't allow us to go into the loop. Make sense? Good. Okay. Second question, which is related. Okay. And second question, have a look at the body of the loop which contains the if statements from line 4 to line number 6. How many times is it going to be executed? N? N minus 1 in this case, right? Because we know the last one of the n checks will give you false. So that means for that one, we don't even go to the loop. So it's going to be n minus 1. Okay, guys, are we okay with this? So anytime if you got anything similar to this, first figure out exactly how many times the body of the loop is going to be executed. I'm just trying to show you how you can analyze it. So once we figure out these two critical questions, the rest will be quite straightforward. Okay? Let's see the rest. So let's now count line by line. Ignoring line number 1, which is just declaring the method. Okay? The first line of the method is really line number 2. Now, line number 2, how many primitive operations can you see? How many? I heard 2, I heard 1. When you said 1, which one? A0, I agree. What about the equals? That means you're doing some assignments, right? You want to get a value first using array indexing and then assign that to some value. So 2, right? So we got array indexing and also we got assignments, right? Again, to make it explicit for you, array indexing is 1, also assignments is another 1, so 2 for this line. Okay, line number 2, it's 2, right? Array indexing and assignments. So now, what about line number 3? Be careful here. You can see line number 3 here. So there are 2 expressions here. The first one is I is assigned to 1. The other one is I less than n. Are they going to be executed the same number of times? Are they? Well, what's the leftmost expression there? I is assigned to 1. It's only to initialize the loop counter, right? It's called initializer, so only 1 time. So that's 1. Okay? And as we agree, I less than n will be executed n times. N plus 1, that's the answer. Are we okay with that? Okay, let me, in case you're not so following, why don't I go back to iPad and show you. So now what you can see is, first of all, we have this expression over here. So we talk about line number 3. So this part over here, I is assigned to 1. It's only executed once. To initialize the loop counter only once. So that means we got 1. And this part here is to check to see if we want to stay in the loop or not. For the very first n minus 1 times, it's going to be true. But for the last nth time, it's going to be false. So exactly, we got n times. So n plus 1. Okay, for line number 3. So for line number 3, we got this many primitive operations. Everybody okay with this? Yes. Question?
So the declaration doesn't matter, right?
What do you mean the question doesn't matter?
The declaration, because on number 2, we haven't declared like.
Oh, decoration, yeah. As you can see in the list I presented in the previous slide, decoration doesn't count. Yeah. Yeah. Okay, so that's about this line here. And let's go to the next line. Okay, that's one assignment and one and comparisons. What about line number 4? So since we kind of try to figure out exactly the worst case. So just think about for each iteration, we're just going to execute the body of this branch, right? Just evaluate it at least. 2 times n minus 1. Okay, that sounds, okay. 2 times n minus 1, that sounds promising. Anyone else? Okay, before I show you the answer, why don't we have a look together? Okay, I'm basically asking over here, let me use a different color, the blue one over here, line number 4 over here. Okay, let's not worry about number of iterations just yet, which we know about, but we'll get that into the context a little bit later. Let's talk about individual primitive operation here for each iteration. This one primitive operation, right? And we do some comparison over here, that's also a primitive operation, so it's 2. And this current maximum is just a variable, so we didn't include it, so we don't count. So that's 2 times 2 primitive operations to be executed for each iteration. As we learned before, how many iterations do we have? n minus 1, 2 times n minus 1. Yeah, that was correct. Yes. Okay with this? Okay. So 2 times n minus 1. Okay, 1 indexing and 1 comparison for each iteration. And we've got n minus 1 iterations. Now, similar, line number 5. So now, since we are talking about worst case, you don't have to worry about maybe in some iterations, maybe we wouldn't really go into line number 5 if the if condition is false. Since we talk about worst case, in the worst case, simply assume the worst case is where line number 5 is executed for each iteration. How many do we have? 2 times n minus 1. Which 2? Which 2? Yes, which 2?
The AI and the equals.
Yeah, the AI and the equals. Very good. Okay, again, if you go back here, we talk about this line here, AI, array indexing, and also equals. Can I just make some little bit change for you, just for fun, okay? Let's say this line over here, rather than having this, what if I have the following? Let's try, okay? I would say current maximum is assigned to AI multiplied by, don't worry about if that makes sense or not logically, I'm just trying to show you how you can count. And then modulo AI. How many? 5 or 6? 1, 2, 3, 4, 5. 5 or 6? It seems like 5 and 6 are the most popular answers so far, right? Anybody got any other answer? Okay, 5 or 6. It seems to me it's 6. Why? It seems to me. I might be wrong, but let's try together. Now, we have 1, 2, and 3. 3 array indexing. And 1 arithmetic, another arithmetic. So far we got 1, 2, 3, 4, 5. And don't forget an equal over here, right? 6. Since it's in the context of a loop body, so that should be 6 multiplied by n minus 1 for this case. Okay? Any question about this? So this exercise here is actually, it shows you just got to be very clear about what the primitive operations are, and then just to count them carefully. Yes?
You said something about declarations not mattering, but when I think of declarations, I think of the equal, like something equals something.
Yeah, so declarations just say this variable is of this particular type, but before you actually assign something to it, the declaration actually doesn't cost anything, runtime-wise. Yeah. Good. Okay, I think we're almost done. Let's finish the remaining lines, and then we'll see more exercise. Okay, that's line number 5. What about line number 6? That one's a little bit tricky. I didn't actually say about plus plus in the list, did I? But how do you figure that out? I heard 2, okay. Anyone else? Why 2? Yeah, that's exactly how it's going to be executed, right? So I plus 1 would be 1, equals maybe another 1. Okay, so basically, let me again, that's very good. Let me go back there. Okay, so now over here you got I plus plus. Remember, this is simply equivalent to I is assigned to I plus 1. Okay, plus 1 primitive operation equals 1 primitive operation. Okay? Good. Let's make it a little bit trickier, shall we? What about over here, rather than I plus plus, I multiply by how many? Just for that particular expression there. Well, to really figure this out, we should know what that's equivalent to, right? Okay, let's do it together. That's equivalent to I is assigned to I multiply AI. And then we got 1 here, 1 here. Oh, sorry about that. I meant to circle this one. 1 here, and then 1 here. How about just one more? Okay, just came to my mind. Okay, again, I want to do this line only. What about I multiply equal A I modulo 2? You can see, right? There's something you can build up as complicated as you like. And this one here, hopefully just plus 1, right? Whatever the answer we got. That's equivalent to I is assigned to I multiplied by A I modulo 2. Now, how do we count? Well, 1, 2, 3, and 4. Okay, 4 in this case. One last one just for fun. Okay. Another one over here. What about I multiply equal A I modulo we're just keeping adding more complexity, right? So that would be whatever answer is plus 1. Because now the right-hand side for the modulo also takes 1 primitive operation, right? So in this case, that would be 5. Okay, guys, any questions about this? You can see the exercise is not difficult. You just have to be very careful and precise. Okay, one more. Line number 6, as we said, and line number 7, how many? 1? Is it 1 or 1 times n minus 1? Just 1, right? Because it's outside the loop already, so just 1. Now, let's summarize what we have got. Basically, in order to count exactly how many primitive operation will be executed in the worst case for this fragment of code, we count line by line. Also, we got some insight into how many times the state condition in the loop will be evaluated, and also how many times the body of the loop will be executed. Now, adding up together, this is the number we'll get, 7n minus 2. So if you got something like this for lab test 2, for example, so that's the answer we're expecting. Of course, we wouldn't just judge by your final answer. We're trying to see how you count for individual steps. Okay? So 7n minus 2 is the correct answer. Okay? So now, one more thing before I take your question. So what does 7n minus 2 really mean? As you can see, this expression here contains a variable, which is n, about the size of the input array. Let's say if the input array is of size 10, that means we got 68 primitive operations. If the size of the array is 50, that means we got 348 primitive operations, right? That's somehow parameterized by the input size of the array. Okay? It's very typical because later on, whenever we argue about the running time for the algorithm or methods is usually predicated upon the input size of the array. Okay, typically n. Yes, I forgot. Yes.
Could you explain line 3 again?
Line 3.
And line 4.
Sure, no problem. Line 3 and line 4. Okay. Okay, let me just go back here, over here. Okay, line 3 and line 4. You know what? It's better to add a new page and then reinsert that diagram. That'll be easier for us. I think it is this one here. Good. Line 3, right? Good. Now, line 3, we know that this is going to be executed just once. So that's 1. And this one over here is going to be executed in the following way. When I is equal to, okay, let me just say, when I is simply just equal to 1, because start with 1 for the very first evaluation, and let's say n is simply just 10, the size of the array. So 1 and then I less than 10, that will just be true. It will remain true all the time until I is equal to 9, and then we still got true. Agree? As soon as we increment I further to 10, it's going to give us false. We know that eventually this expression must evaluate to false, otherwise we got infinite loop. It's not going to happen, right? So that means we got exactly 10, which is just n. Okay? So now we got 1 and we got n, so it's n plus 1. That's for line number 3. Okay. For line number 4, it's kind of related because we know that from this diagram over here, we know that exactly this many times I less than 10 will be evaluated to true. That's exactly equal to n minus 1, right? So now we know that whatever, let me see, line number 4, okay? Each iteration, we're going to execute this line. How many primitive operations are there? As we learned before, we have this one, this is 1, and this is another one, so 2 for each iteration. But now we know that exactly we got n minus 1 iterations, so that's how we figure out. Yes, question?
Yeah, so the reason we counted 1 for 7, you know, for the 7th line where we return current max is because current max is equal to an array index, right?
No, current max is the, no, it's, I would be, no. Current max is the maximum value in the array, yeah.
So then why did we counted primitive type for 7, line 7, didn't we?
We did, yeah, it's just 1.
Okay.
Just 1. Yeah, so I'm not sure what your question exactly was, but
Why that we counted primitive type?
yeah, exactly. You can see line number 7 here, it just return, right?
Oh.
However, be careful, be careful. Since he mentioned it, let's do another variation over here. Let's say hypothetically, if I say return a 1, how many primitive operation do we have? 2, right? 1 here, and return is 1, so 2.
I didn't know return.
Yeah, return also counts, just return, right? Good, let's go to next slides. So now given that we know about how to count precisely the number of primitive operation given any code, let's talk about running time. If we know that 7n minus 2 is the number of primitive operations, let me just put it here. We know that it's 7n minus 2. Hypothetically, let's say if each primitive operation will take exactly 2 milliseconds, let me just assume. In that case, we know that in the case where input size is simply equal to 10, in that case, we can say 68 multiplied by 2 milliseconds will be exactly the absolute time that will take to execute this method here. Agree? But the 2 milliseconds here is not really that useful for our analysis. For example, let me say this. Currently, we have only, let me just put the add page below. Let me say this. Let's say I have method number 1 and method number 2. Let's say we applied a similar exercise. Method 1 is simply 7n minus 2. Let's say method 2 is something similar but not exactly the same. What about 8n plus 9? Okay, let's say that's how we count it. So now in order to really compare these two methods, if you really want to calculate the absolute time, first of all, you want to know how much time it would take exactly for each primitive operation. Let's say 2 milliseconds. So what you will get is, first of all, let's say input size is 100. And also, the running time for primitive operation, let's say 2 milliseconds. Let's say this is already given to you. So now we can definitely compare to see how much time it would take, right? Just apply 100 to here, and also multiply by 2, and then you will get units in milliseconds. However, it's not really that necessary, right? Because you can see we can easily factor out this 2 milliseconds from both of them, and we just can ignore the amount of time for the primitive operations. So what does that mean? That means up to here, we talk about the absolute running time, which is milliseconds. In order to compare which one is more efficient, we don't have to go that far. All we gotta do is simply compare 7n minus 2 versus 8n plus 9. That'll be enough. Whatever exact amount for the primitive operation to execute for a particular platform is not relevant over here. So now that here's a conclusion. Whenever you want to compare the running time for any given two algorithm, once you know about their primitive operations in terms of the input size n, you're done. You don't have to really worry about the exact running time for a particular platform. It's just not going to help you. It wouldn't lead you too much further. Okay, let's go for some slide, and that's the idea. Exactly what the idea is about the next slides. Okay, so now the primitive operation is going to be some constant and some basically the same, so we can ignore that for our comparison. Okay, so now let's say in the case of the find max, we got 7n minus 2, and then if you want to calculate the exact time, you just say that multiplied by t. But t can be any number, 1 milliseconds, 2 milliseconds, or 3 milliseconds. Doesn't really matter. So now the conclusion is, if you want to compare two different running times, you can simply ignore the common factor t. Okay? So now, from now on, we're only going to focus on the number of primitive operations. Any question about this up to now? Okay? So up to now, we are being very precise about how many primitive operations you're going to execute for your code. But now we want to go a little bit further. We want to do a little bit more analysis. Let's say 7n minus 2 versus 10n plus 3. It seems like maybe the right-hand side, 10n minus plus 3, is more expensive. Seems to be a little bit more inefficient. Seems to be. However, when we talk about very large input, it turns out it doesn't matter that much. So it is so-called asymptotic analysis. So we are really talking about, over here, let me give you a little bit preview, a conclusion, and then we'll get to the math part. Okay? So for these two over here, we'll say asymptotically speaking, they are the same. Which means we're talking about n over here gets to infinity. Then these two algorithms really make no difference. They're both linear. Okay, you can see the reason they're linear is you can see the power over here is simply just 1. That's why they're linear. Okay, but we'll get there. On the other hand, if you have another algorithm that looks like this, for example, n squared minus 2, right? In this case, you can see the power over here is strictly larger than both of them. So asymptotically speaking, we say this algorithm is more inefficient than the other two. One more example. What about another one? We say log n. In this case, log n also, asymptotically speaking, will be considered as more efficient than just linear over here, or even constant. Sometimes we may have, let's say, just 8, for example. That's another running time. So what does a really equal to? A is a times n to the power of 0. And now in this case, you can see 0 is a strictly smaller power than the power of 1. So that's considered as more efficient than the other one. I'm just sketching the example, but we'll see exactly my points in later slides. Any question about this before I move on? Yes? How about this? I would suggest, let's delay it. I was just kind of sketch the idea as a preview, but we'll see exactly the diagram in just a moment. Okay. The reason is, visualize how the how 7n minus 2 versus n squared minus 2. How would their curve look like? The n squared minus 2 will actually the slope is much steeper as opposed to the linear function. That's kind of the intuition, but we'll see. Yeah. Yes?
Right here, when you talk about like asymptotic, that they're the same,
Yeah.
and the other ones are not the same.
Mhm.
Talk about the fact, like we're comparing how fast each one going, right?
Yes, exactly. We're basically comparing the slope or the first derivative of the functions. Yeah. Okay, good. Let's go to the slides and then let's get more explanation. Okay, let's just mention something here. So we have, let's say 7, let's go over some terminology, okay? If this is a running time we got, 7n minus 2, so n is simply power of 1. you can think about it 7 times n to the 1 minus 2 times n to the 0. Agree? Okay. Now, you can see we basically got 2 terms over here. One is with n to the power of 1. The other one is with n to the power of 0. Okay? Which one is higher? Apparently, this one is higher. So we'll say all the others are the lower terms. Okay? Let's go over some terminology. N is the highest power because of power 1. Okay? And then 7 and 2 are the multiplicative constants. Okay? And also we got 2 over here, which belongs to the n to the power 0. That's called a lower term. Okay? Just some terminology here. And then when we really try to compare to running time, basically only the highest power matters, asymptotically speaking. When the input size gets to very large, you only worry about the highest power in the input function, the running time function. Let's see more example. Let's say 7n minus 2, how do I actually get? Okay, let me just go there. Go to iPad and then show you. And then we'll just talk about it more formally. Give me one moment. I'm going to introduce a new page. Let's see over here, 7n minus 2. Okay, so this is what we can drop. We can drop, first of all the lower terms. This is the higher term. So drop all the lower term. And also for the highest term, also drop the multiplicative constant. So we only got n left. Okay, that's one example here. And then we got another one. What about this one here? What is it going to be after we drop all the multiplicative constant and we drop all the lower terms? N squared? Agree? Well, if you try to arrange that from the highest to the lowest, you got n squared, 3n squared plus 7n plus, actually, I should really, let me say that again. If you arrange that, 3n squared plus 2n log n plus 7n, right? So drop all the lower terms, which will be the previous two. And then drop the multiplicative constant, you got n squared. Okay? Question about this. You okay? Good. Oh yeah, okay, basically, exactly, that's what I said. Okay, if you have no question, let's get to, we're getting somewhere, okay? So now let's just go over the very common running time functions that you're gonna see, okay? Not just in this course, but also maybe in 3101 in 2011, okay? So now, up to now, our mini conclusion is whenever we want to analyze the running time of any given code or method, we want to assign some mathematical function to the fragment of code. It could be, for example, the running time can just be 5, which is pretty much like a 5 times n to the power of 0. If your method can work in this way and being correct, that's the best case, constant time. That means you can see that over here. Let's get some intuition here. 5 here, you can see there's no occurrence of n. That means it doesn't matter how large the input array is. You'll always just be 5 primitive operations you need. That's a very good method. The second one is a little bit more expensive, but not too bad, log 2n. By the way, whenever we talk about log, for this course over here, it's base 2, not base 10, because computer is binary number, so base 2. Log 2n is also very nice. We're going to talk about something called binary search a little bit later when we talk about recursion. That's this kind of a method. Okay? That's logarithmic. And also we got linear. Okay? And also we got quadratic. And also we got cubic. And also exponential. Exponential really is the worst running time can get into. It's so-called brute force algorithm, which means they try out all the possibilities. Okay. All right. Now, let's just show you some diagram over here. You can see for the same algorithm, you may have different input size A, input size B, input size C, and etc. Right? But now, basically what we're doing is we are trying to figure out exactly the worst case scenario. Okay. Is it useful to actually talk about best case scenario? Intuitively. Not really, right? Because let's say if I want to sort an array of number, what's the best case?
That they're sort already.
It could be it's already sorted, or what about empty array? If the array is empty, nothing to be sorted. If the array is of size 1, Also nothing to be sorted. That's the best case. So it's not very useful to talk about best case. And for the average case, let's not worry about it because best case, sorry, not best case. For the average case, we don't worry about it for this course. Average case will actually rely on some probability theory that you learn from also 2030 about math. Okay, so let's not worry about it for this course. So we only worry about the worst case. What can be happen in the worst case? All right. So now we're going to talk about asymptotic analysis. So what's really asymptotic analysis? Which means the input size grows very large towards the limits, towards infinity. Okay, that's basically what we're doing. And then, now let's say again, if, we'll get to the proof for this, this kind of reasoning, but let's just get some intuition. Let's say I got running time n, which is linear. Also, I got another running time, which is quadratic, right? N squared. Which one is more efficient? Well, n, right? That's a lower power. Good, very good. Very good. It's always compare the relative performance. Let's not worry about any absolute running time. Okay? It's been factored out already. Okay, so now you always just compare the higher term. Okay, so now let's have a look at this. We'll prove this a little bit later, similar example, but let's have a look. Running time number 1 is like this, and running time number 2 is like this. You can see that even though they don't look the same, for sure, but asymptotically speaking, because their highest power is both 2, so that means they're asymptotically equivalent, equally efficient. On the other hand, if we got something like this, you can see that for here, the first one is n cubed being the highest power, and the second one, n squared, is the highest power. Asymptotically speaking, the second one is more efficient. Okay, has lower power. Okay. So, guys, any question about this until now? Before we get to something a little bit more formal, we're going to do a little bit proof. Yes.
So the lower the power, the lower the exponent.
Yeah, the lower the power, the better. The more efficient your algorithm is. Of course, the best case, constant, right? That means the power is simply 0. Good. So now, there are basically 3 formal notations to study about asymptotic. It's called asymptotic bounds. We're going to study this for this course, called a big O, capitalized O. Okay, that's what we're going to study about. And there are another 2. In case you're interested, feel free to look it up, do some research by yourself. But for this course, we only need big O. Another one is called big omega. The other one is called big theta. Okay, big O. Now let's talk about definition. Okay, so this might be a little bit dry, but let me try to make it hopefully easier to understand. Okay, so now let's go to iPad over here before I show you the slides. Okay, let's just study some definition very quickly. Okay, so basically we talk about 2 functions over here, mathematically speaking. Let's go very slowly. Now, we have one function called f of n, and we have another function, let's say g of n. Okay, now how the way you can think about f of n is like this. Think about f of n as the running time of your algorithm or method, f of n. And now we want to find out what's the closest asymptotic upper bound for f of n. And let's say if we argue that, if you try to argue to me the asymptotic upper bound, big O, for your input for your method function f of n is simply g of n. It must satisfy the following criterion. Okay, let's try. In order to prove it, you have to give me 2 things as witness. Okay, one is a constant. Let me just use highlighter over here. One is a constant c. Okay, another one is a starting point of the input size n0. So these are the 2 witnesses. Okay, and once you give me these 2, you have to show to me that the following equation actually holds. Let's get some intuition just from the equation, and I'll show you in the I'll visualize it for you. Okay, and we'll also use some example. Now again, let me just get rid of highlighter over here. Basically, what we are saying is, f of n is the running time of your algorithm. And G of n is what we argue the asymptotic upper bound of your algorithm should be. Okay? And then C is simply some constant that we show, that we actually choose. And then this less than or equal to relation over here, I'll just call that upper bound effects. Okay, how is that visualized? Let's have a look. So now let me just use highlighter to show you. Let's say let me make it a bit thicker. This is the function for my running time to start with, the green one. Okay? Now, if I want to find its upper bound simply means I want to find some curve such that f of n is constantly below that particular curve, right? That would be lower. It's exactly this g of n, okay? Over here. Okay? More precisely, over here, you can see that over here, it is g of n multiplied by the constant over here. This is c over here. You can see over here, starting from this point. So this is the point after this point. We have the upper bound effects, which means we have f of n, which is over here, less than or equal to c times g of n. Okay? But what about before that point? As long as we can show this such a point to start the upper bound effects, what happens before that, we don't care. It could be the reverse. You can see before this point over here, this point over here, you can see it's the opposite, right? F of n can be the upper bound for g of n. That's fine. As long as after this particular chosen n0, we have the upper bound effects, we are okay. Okay, any question before we go over one example to strengthen your understanding? Any question here? I know it's a little bit dry, but anything that's not clear about the definition here? All right, let's do one example, okay, right away. Now, let's say this is my f of n. It's an plus 5, okay? And I claim that, of course I gotta prove it. I claim that f of n is big O of g of n. This is what I claim. How do I prove my claim? As I said before, I need to choose a c and also some starting input. Okay? Now, let me say I simply choose 9. And let's find out what n0 is. As soon as we find it, we can see the trend, and then we prove it informally. Okay? Let's see exactly how we do it. Okay? Let me just use an animation on the slide to show you. Okay. So that's exactly what I said on the slides over here, but let's now just go over one example. And then if you've got questions, we can take your question. Okay, so now we want to prove, okay, this is what we want to prove. My input function is an plus 5. That's my running time. And then I want to prove that it's big O of n. That's what I want to prove. How do I prove that? Basically, I got to choose constant c and also n0. Let's say I choose c to be 9, exactly what I said in the iPad. Let's just draw some table. Okay, let's try that. Of course, input size like array must be non-zero. Well, it must be non-negative, right? Starting from 0 and then 1 and then 2, right? Discrete size. If we choose, so you can see over here, an plus 5 is the running time for our algorithm. And 9n is actually c times n, right? You can see c, we chose that to be 9. Okay, let's fill out the table and get some feel. And now, do you agree with this row? When n is equal to 1, plug in 1. And then we got a plus 5, 13, and 1 times 9 will be 9. Do we have the upper bound effect yet? No, because if it's upper bound effect, an plus 5 must be less than or equal to 9n. So we're not there yet. Increase the size, which means where are we? That means we are basically here. That means we are still in this region over here. right? We're getting there, okay? Okay, let's say n is equal to 2. We got 21 and 18. Getting a little bit closer, not there yet. What about 3? Even closer, not there yet. What about 4? Not yet. 5? Yes. You can see the growth over here. You can see as soon as n, the input size is 5, that means both values will be 45. So now we got exactly 8n plus 5 less than or equal to 9n. But does this trend go on forever? If it doesn't really go on forever, then it cannot be an asymptotic upper bound. Let's just try a few. 6, okay? When I say dot, 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 that means it's really going to go on. Okay, so I will let you try a little bit more. Okay, let me just apply this example over here and then show it to you. Okay, thinking this way here. So now let me plug in a value over here. So now what I can do is over here, we talk about this function over here, 8n plus 5. Of course, that's more like a linear. It shouldn't be curved, but hopefully you can just see the idea. 8n plus 5 is the input function we like to show. Okay, and then we claim that this particular running time function for our algorithm, its asymptotic upper bound should be just n. That's what we claimed it to be. So the way we prove it is by choosing a constant factor over here, 9. And that's exactly this function over here. So that means over here is simply 9 times n. But as we can see from the table, the upper bound effects doesn't happen right away when n0 is equal to 0. It doesn't really happen that way. What happened was, it wasn't really until when input size is equal to 5 that we actually got both of them being equal. And then after which we got the upper bound effects, like that. Okay, so now you can think about over here, n0 over here is exactly just 5. After 5, we do have the upper bound effects. Before that, we don't. Guys, any question? Please ask. Yes. How do you choose it? Good question. I tell you what, it's very easy to choose it. I will show you some strategy. So now, you know what I'm trying to show you now? I tell you what C is already. I'm showing you given C, how do we prove it? But in a few slides later, I'll show you a strategy to choose a C that's always guaranteed to work, mathematically speaking. Yeah. Yes? Sorry, say it again? Good question. Are our functions always going to be linear? No. Sometimes it can be constant, it can be quadratic, can be cubic, can be anything. Very good question. Okay, yeah. Well, since that chalkboard there is not really on the iPad, so yeah, that's okay. So the f of n, you can see that, okay, one thing to note. Let me just, over here. You can see for the definition over here, I didn't say f of n must be linear or constant. That means it can be any arbitrary function. So when you want to decide the asymptotic upper bound, you have to decide what it should be. Again, it's not constrained to linear or quadratic. So it really depends. So over here, I'm just trying to show you the idea in general. I'll see more example in just a moment. Yeah. Good. I would say most of the methods that you used to write back in 1022 are either constants or maybe linear. Maybe sometimes quadratic. You rarely have to write anything as cubic. Okay? But once you get to 2011 or 3101, you might see log n quite often. Because every time you see log n, that means you're doing something very clever in terms of arranging the things. But we'll get there. I'll give you some example a little bit later. Okay, very good. So now, let me ask you this question to, yes, question.
Okay, so when we're using big O notation,
Mm-hmm.
would you say like we're using to compare functions to see which one is most efficient with that?
Yeah, so the reason we're using big O is as follows. Let's say I got two algorithms. Okay, very good question. So the question was, what's the use of big O, for example? Let me just give you a little bit preview, okay? Let's say I got running time number 1, which is, let's say 7n minus 2, okay? I got another running time let's say running time 2. That's 6n squared minus 100, for example. Okay, well, just theoretically speaking, okay, yeah. So now, let's say I got these two running times. In order for me, okay, I told you informally, you can simply drop all the lower terms and multiplicative constant. You know right away this should be more efficient, right? The more formal way to argue about it is you can say, you can say this one here is big O of n by using the proof that we just showed it to you. And this guy over here is big O of n squared. That's the tightest bounds. And this has higher power than this, so that's why this is more efficient. That's how we use it formally. Yeah. Because you don't want to just tell people that you just drop the lower terms and give them and drop the multiplicative constant. You want to be a little bit more formal how you derive the upper bounds. So big O is the way to go. Okay? Questions?
Are the exponential functions the only ones that would have a non-deterministic polynomial type?
Say it again.
Would the exponential functions be only class of
Yeah, I would say, yeah, for the purpose of this course, I would say you can imagine yeah, so exponential, yeah, there's like a 2 to the power of n, just to, not to get things too complicated.
So like nothing else would be NP?
No, we don't want to get there. Yeah, just exponential. Yeah, exponential simply means you want to try out all the possible branches to figure out your solution. Yeah, for NP, maybe when you get to 2001, you'll learn about it. Yeah. All right, let's go back to there. Now, let me ask you one question. So the way we proved an plus 5 is big O of n is by choosing c to be 9 over here, right? That's how we did it. And n0 is actually 5, right? That's how one way to prove it. Now, another question for you. We can also prove the same claim by choosing c to be 13 and n0 to be 1. So that means there's more than one way you can prove about a claim. But how do we see that over here? When c is actually 13 over here, so that means we're going to say 13n in the table, right? That means when n is equal to 1, an plus 5 is still 13. And 13n will be 13. So we get the equal right away. And then after that, we got the upper bound effects. So that's the second way of proving it. That one seems to be a little bit easier for us. But again, back to your question, is there a good strategy for choosing the constant c, multiplicative constant? Yes, there's a way. Okay, we'll see that. Okay, let me just go through a little bit more definition over there, okay, about big O. Okay, so we have covered up to now. Okay, so given some running time function, you want to decide its asymptotic upper bounds. And this symbol over here is membership. Okay, so this is what you can think about. Okay, let me just do another diagram to show you that will also be related to some later slides. So when I say big O of n, so this is really like a collection or a set of functions. Okay, for example, you can think about this whole set denotes the family of functions for big O of n. So what do they contain? They contain, for example, n minus 2. They contain n plus 2. They contain 7n minus 2. They also contain 3n plus 4, etc. Why? Because you can easily prove that, as we did before, n plus 2 has the asymptotic upper bounds being n. If you can prove it, that means n plus 2 is in this family. If you can prove that 7n minus 2 is also has the asymptotic upper bound being n, you also prove that it's in this family. Okay? So that's why when I say 7n minus 2 is big O of n, what I'm really trying to say is it's a member of this particular function. Okay? Just so as to show you. Okay.
So is it like area ax, an plus b?
Correct. That's correct. So it's a very good observation. That means any ax plus b should be in this family, right? Not only that, any b is also in this family. For example, let's say if you have a constant function like 8, always return 8, that's also in this family. Anything that's of strictly lower power or equal power is in this family. Okay? Now, question for you. When I say something like this, 7n squared minus 2 is big O of n. Is that true or false? False, right? Because thinking this way, it's very easy for you to check intuitively. For this one here, the power is 1. For here, it's actually higher power. So that means it doesn't belong to the family. Which means when you say 7n squared minus 2 belong to this family, that's not true. Okay? There's no way, how do you actually somehow argue that formally? There's no way for you to choose a constant, multiplicative constant for n, such that, for example, if you choose 1 million, for example, or 1 billion, doesn't matter how large you choose it. Once you choose it, you will never have the upper bound effect starting from some points compared with this function. There's no way, okay? Because strictly higher power. So when things go towards the limits, this is just not going to happen, the upper bound effects. But we'll get there. It's one of the rules you have to know. Okay, so just there are different ways for you to say it. You can either say f of n is big O of n, or you can say f of n is a member of, okay? Yeah? Or you can say a little bit even more formally, you can say it's order of g of n. That's also fine. Yes?
So for big O, you say for n to be the linear function, like 1 or less, right?
Correct, yeah.
So
either the same power or less power.
So if you had like 7n to the negative 1 or 7n to the negative 2, what sense would that be quite a bit?
So basically, okay, interesting. Mathematically speaking, right? Okay. Yeah, so I see what you mean. Yeah, it is. So what David's observation was 7n to the, yeah, that's fine. That's fine. Because negative 2 is strictly lower than the power of 1. Of course, that will be including the family as well. Yes, indeed, mathematically speaking. Although I'm not sure if you might get any algorithm like this. Yeah, right? That's okay. Okay. Let's now go on. Okay, let's do, let me see if the next one is the sign. Okay. Now, if I give you this proof to do, how would you choose C and N0? Of course, this is the example where I want to show you, you don't want to just guess and then do the table. That's not the way to go. I want to give you some motivating example to say, there's a way, there's a strategy that will always work. Okay, how do we choose? We want to choose a constant C, right, over here, such that the upper bound effect is going to happen at some point. Yes, David?
Is it not easier to just choose a very high C and not worry about it?
Yes, but that's true. Of course, you can always choose a million, right, hoping that I wouldn't give you anything, right? But I would say that's not so nice, yeah. But you're right. If you choose a very large constant, of course, you might just start to work right away. Yes, I agree. But let's try to choose just big enough. Yeah, I agree with you. Yes.
Put n equals 1 into fn and calculate out and put that as our C.
So what value would you choose for C?
In this case, 5 plus 3 plus 2 plus 4 plus 1.
Okay. So basically, what he was saying is the strategy is we'll prove in the next slides very quickly. We want to choose the smallest C value over here such that the upper bound effect is going to occur when n0 is just 1. Okay? That's the smallest one we can choose. Okay? Now, in this case, you can see, look at the multiplicative constant over here. We got 5, we got 3, we got 2, we got 4, we got 1. Add them up together, and you will simply get 15. Once you get 15, choose C to be 15. It's guaranteed n0 is going to be 1. Okay? But you can prove this informally using the table by yourself. Okay? What I want to do is to go to the theory. Okay? Well, even though I call it a theorem, it's not really that complicated. But let's look at that very quickly. Don't be too terrified by the math over here. Okay, let me try to go over that. Okay, let's say this is our running time function. And it simply goes from the lowest power to the highest power. And the d over here can be any number. It can be 1, it can be 2, and it can be any number. It can be up to 10 as well. Let's say I give you this input function over here. Oh, by the way, the A0 over here A1 over here and AD over here, they can be positive, they can be 0, they can also be negative. So now, let me tell you the conclusion right away, and then we prove that very quickly. How do we choose C and N0? This is the answer. Notice the vertical bar over there. Hopefully you know what it means, right? Absolute value, okay? Because the multiplicative constant might be negative, if we want this strategy to always work, we always add up all the absolute values for all the multiplicative constants. That would be the C. And I would say almost always N0 will be 1. When I say almost always, that means there might be some exception, which I will show you. Okay? But the strategy will work almost 99% of the time.
Why is it absolute?
The reason is because the A0, A1, so these multiplicative constant might be negative. So that means, for example, let's say if let's say this is 5, this is minus 2, that's minus 2, etc. So if you don't have the absolute value, you will just get some negative value for C eventually. That wouldn't give you the upper bound effects. Okay? So absolute value is really important. Okay, how do we prove this? Okay, I just want to show you something very quick, okay, to get an idea. Okay, let's go to iPad over here. So there are only 2 questions I want to lead you to think about the proof. Okay, you can read the proof on the slides. Okay, okay, let's review very quickly what we got. So this is our running time function over here. So starting from the lowest power until the greatest power. And D here can be any number, okay? And then we have also the multiplicative constant A0, A1, and up to AD, which might be positive, 0, or negative, okay? So now what we want to prove is the follows. We want to prove that f of n is big O of n to the power of d, which is the highest power. How do we prove this? We follow basically the same process as before, but now we're just arguing for all the cases in general. Okay? This is what I said before. We choose C to be the absolute value over here, and we choose the N0 to be just 1. Okay? So there are basically 2 questions we got to ask ourselves very quickly. The first one, let's look. Because we claim the N0 to be 1, does the upper bound effects occur already? Why don't we try? Okay, plug in the number very quickly, okay? I'll try to write quickly. So now basically we're going to get, for the left-hand side, f of 1, we got basically A0, n to the 1, plus A1, n to the 1, plus all the way to AD, n to the d. Actually, just 1, right? Yeah, exactly. Sorry about that. Yeah, keep making mistake. What I should do is, I should really, hopefully that's might be, maybe, I should say 1 to the 1, 1 to the 2, and then 1 to the d. Agree?
No. I mean, like, it should be like A1, 1, 1.
A1, 1, 1, A2, A1, yes, you're right. Why am I doing this? A1. Sometimes I thought, do some illustration right on the fly might help you understand. Sometimes it might confuse you, right? I try to practice, yeah, okay. No more mistake. No more mistake. A1, 1, 1, and then AD, 1D. Good, okay. That will be the left-hand side, okay? Plug in 1, okay, here. And then what about C over here? We know that C is simply this number over here, okay? And then C multiplied by 1 to the power of d. But let's multiply 1d over every term in the C. So what do we have? What we got is, it's going to be A0, which is the first one, multiply 1 to the d. First of all, agree? And then plus absolute value for A1 multiplied by 1 to the d, plus all the way to A, d, absolute value, and then 1 to the d. Agree? Okay. Can I safely say less than or equal to?
Yes.
Yes, right? Okay. First of all, you can see A, that's why absolute value is really important over here. This is smaller than or equal to that. This one also smaller than or equal to that. Absolute value, guarantee. And then 1 to the power of 0 and 1 to the power of d, the same. it will just be 1 anyway. Okay? That's for the case of input size 1. So at least we proved that N0 is going to be the starting point for the upper bound effects. But is it really going to persist for the effects? That's why we got to plug in a number and do this. Okay? To really make sure you don't really get bored, why don't I just show you on the slide quickly? Okay, that's what we just showed on the iPad. Hopefully you get an idea. Now we're just plugging different terms into the equation. What we will get is something like this. So you can see that over here, we got n to the 0, n to the 1, and n to the d. I'll only show you one thing. You can see over here, n0 is less than or equal to n to the d. You agree? Well, because we talk about n being larger than or equal to 1, of course this is going to hold. Okay? So these are the proofs for this theorem here. But I'm not going to test you about the proof, but hopefully they can give you some insights. But the conclusion is, now from now on, if you want to prove about a running time function has the following asymptotic upper bounds for big O, you can choose the C and N0 following the theorems. However, I got to warn you, in some cases, N0 may not be exactly 1. That's why you got to be careful. Do not just apply the formula blindly. Okay? That's why we got to go over some example, which hopefully we can do in 5 minutes. Okay? And then we are done. Not yet. Okay, you know what? I will go over these slides maybe just next time, but I want to go to examples right away. Let's try to apply the formula, okay? I think 5 minutes will just give us enough time. Okay, let's try. What I will do is I'll just add a new page first of all, because we do need for one of the example. First of all, what's the asymptotic upper bounds for big O? It's big O of n squared? Highest power, good. Now, how do you choose C? Well, 15, right? Well, actually, it's the same example. So 15, and then N0 is 1. That's fine. Now, one more. How about this one here? Well, choose big O of what first? N cubed, right? Good. And then we can choose 35. We can just say 20 plus 10 plus 5. Okay, 35, very good. What about this? This one, I can tell you what, this one is tricky. First of all, what's big O? Big O of what? Big O of log n, very good. Okay, now, question for you. What should be the C? 5, 5 is fine, 5 is okay. If I choose 5, what's N0? Can it be 1? Huh? Oh, did you say 10 or something? No, okay, yeah. Yeah, what's N0 in this case? Can it be 1? Let's figure that out. It turns out it cannot be 1. Why? Let's see exactly. Okay, let me have a look at that. Think about why 1 cannot be the case, and we'll figure this out quickly, and then we are done. I'll put it on the iPad quickly.
It's going to be 2 less than 0.
Mm-hmm. Okay, let's have a look. So log, we talk about base 2. So this is f of n. If we claim that this is big O of log n. Let's say we choose C to be 5. That means we are basically considering 3 log n plus 2. And also 5 multiplied by log n, right? That's what we have. And let's use a table to help us. Now, can we see, let's say, what about N0 over here? And let's say N0 is equal to 1. Then what do we get? What's this? What's log 1? You know why, right? Okay, so I don't need to repeat that. Okay, 2. What's 5 log n? 0. Do we have upper bound effects? Nope. When you say less than or equal to that, that's not the case. What about 2 over here? 5, right? What about here? 5, yes. Starting from here. That's the only trick. So that means in the lab test, if I give you anything involving log, be careful. The starting point may not be just 1. Okay? Okay, I'll stop here and then we'll continue from Wednesday. So for lab number 3, I'll be in the lab session to help you today.